Okay, so I'm going to split the lecture of today in two parts, a little bit of a review, and then I will build. So the first part is actually really a bit review of some things that I will need in the second one. And I remind you first about symmetric matrices. So we are talking here about square matrices, right? So A is an n by n matrix, and n can be any number here, but we will often only do 2 or 3 or something like that. Okay, so remember a matrix is called symmetric. What does that mean? That it is equal to its own transpose. So an example, for instance, 3, 4, 7, 4, 7, 2, 0, 0, 1. So what is the transpose of this matrix? That would be, so this is, if this is A, let's write down A transpose. So we would take this row and make it into a column. And then take this row and make it into a column. Take this row and make it into a column. But of course, this is exactly the same matrix. Another way of seeing this, I think I told you last time, this is from 1.7, right, the symmetric matrices, is that you can visually see this if you have a diagonal here, and it's symmetric around the diagonal. So, I mean, if you flip over the diagonal, you see these two correspond, the 7s corresponds, the 0s corresponds. Okay. So it is relatively easy to recognize that the matrix is symmetric. Okay, so that's one thing that we're gonna need. Because in part 2 we will really only work with symmetric matrices. Another thing now that I want to remind you quickly of is we had the inner product of two vectors, so in Rn. So if we had two vectors u, then we defined u times, so vectors u and v are vectors in Rn, then we defined this product uv. And let's do this on an example. For instance, in n is 3 here, how did it work? Well, suppose u was 1, 2, 4, and v was -1, 3, 2. The product would be, you take the product of the first two elements, -1, product of the second element, plus 6, and the product of the next two, and add this all up. So 12 plus 1 minus 1 is 11. Okay? Now, we have seen that most of the time we like to write our, when we work with matrices, write our vectors as columns. So let's rewrite these two vectors that I had here as 1, 2, 4, and the column 1, 2, 4, and the column -1, 3, 2. Okay, so what I was doing is I'm multiplying, remember, the first two elements, the two second element and third elements. But if you think about it, this is exactly the same as what you would do if you, I want to take the same, okay, yeah. So if you would do this one, let's take, suppose, okay, bear with me. I said I'm going to make them columns, and now I'm going to the first one write this as a row, and the second one as a column. Now, so what do we have here? Let's work down. This is a 1 by 3 matrix, right? And this is a 3 by 1 matrix. Remember, the first number is the number of rows, the second one is the number of columns. And we know that if we multiply these two, then we get a 1 by 1 matrix, which is just a number. And that's exactly what this is, right? If you work this out, it's the same principle. You go to you take the first two elements and multiply them, the second elements and the third element, etc. Okay. So the way that we calculate it is exactly the same. Now, I still insist on having my vectors as columns. Well, you said, yeah, you're gonna protest and say, yeah, but you wrote it here as a row. Well, okay. So that's not my vector. That's the transpose of my vector. Remember, what's the transpose? Is that rows become columns, columns become rows. So I hope you see that this row here, 1, 2, 4, is the transpose of this column. Okay? So what am I saying? And this is just V, right? So what I'm saying is the dot product, the inner product that we called it, or I think we called it only inner product. Wait, let me double check here. What do we call it? No, we call it dot product, sorry, yes. So I'm gonna, let me call it the dot product here. because it's a dot, right? We use a dot here. What we show now is actually the same. So sorry, let me do this in general, right? I did this on an example, but if you think about it, it's exactly the same. Is you take the transpose of the first matrix. You think of these as columns. You take the transpose, so it becomes a row, and multiply it with the other guy. So this is now regular. So it's a smaller dot. So this is a big dot from the dot product, right? Dot product, and this is just multiplication of two matrices. So that's how this dot product can be thought of as a product in matrices. Now let's see what happens if another thing that we discussed about was that if A is an n by n matrix, then we can think of it as a transformation. So we have a transformation here that depends on this matrix. And how did that transformation go? Well, it took a vector u and you just multiply it. Okay? That's the transformation that corresponds to the matrix A. Sometimes we just write A for the transformation. Okay. So let's now mix these two things. We have a matrix and two vectors. Still a u and v as before. What is the dot product of this thing? Let's try to figure out whether we can find a formula for this. Okay. Right. So what we have is here, we're going to use this formula here. Let me box it a little bit. So in a bit, I'll put it in a different color here. So this is the way that we can rewrite a dot product in terms of matrix. So that means of the first vector, remember this is just a vector, right? The result is a vector. Again, and this is an n by n matrix. You multiply it with we now think of these things as n by 1 matrices, columns. And then the result is again an n by 1 matrix, a column. Okay? Alright, so let me get rid of these little green thingies. Okay, so I take the transpose, I'm using this formula, right? I take the transpose and then multiply it with V thought of as a column. Okay. Now, what's the transpose of a product? Again, go look it up in the chapter on transpose. It's the transpose of the factors, but in the opposite order. So it is, this is a vector. You take the transpose of U, you then take the transpose of A. So you see the order has flipped, and then we take V. Okay, and these are all just matrices multiplication. So I'm going to group the two last ones together. And we'll write it as this. Okay, so still matrix multiplication, right? But look, this is again the same as this formula, except now, okay, I have a u there, but the back is now not v, but atv. So this is actually the dot product of the vector u with this vector. Okay? And so this is our second formula. Let me write it up again. The second formula that I want to use is that au dot product v is the same as the dot product u a transpose v. So if, in other words, what it says is if you want to move a matrix through a dot product, you have to take its transpose, right? That's how it goes from one side to the other side. So it goes here from this one side here to the other side by but then in the meantime you have to transpose. But now going back to these symmetric matrices. In a symmetric matrix it doesn't matter. So in particular, so if A is symmetric, then we have that AU dot V, the dot product, is the same as U dot AV, because the transpose is equal to the matrix. So in this, in the general formula there has to be a transpose, but if they are the same, it's a simplified formula. So that's what we have here. That's what the reason is why we would do symmetric, why we're interested in symmetric matrices. They have this nice property. Okay, so I said this is a bit of review. The first part is symmetric matrices, 1.7, and this 3.2 is actually, this is the formula that you can find on page, if you want to see again, this is on page 152 in the book. But okay. So next review, so no, not review now, it's 7.1, is orthogonal matrices. So this is a new concept. So as you noticed, it's a lot of definitions here, and that's why this is a preliminary video here. We're not going to do really much exercises here. So what is an orthogonal matrix? And before I even do that, I'm going to just work with an example, show you something. Okay, so this is 7.1. I'm going to take this example. Okay. Let's look at the following matrix. Now, be careful. It's going to be a slightly uglier matrix. It's a 3 by 3. 3 7s, minus 6 7s, 2 7s, 2 7s, 3 7s, 6 7s, 6 7s, 2 7s, minus 3 7s. Okay, now as I said, it's a bit ugly in the sense, let me make the same shape, like 3 7s like this. Okay, this is a 3 by 3 matrix. So what can we say about this matrix? Is it symmetric? No, it's not symmetric at all along the diagonal. So there's some, you see some pattern, some symmetry in there, but that's again not really what is going on here. So what is happening here is let's multiply this. What's the transpose? So it's not symmetric matrix. Okay, we agree. Now I'm going to calculate the following thing. I'm going to calculate A times A transpose. Okay, just bear with me what happens. So this is 3 7s, 2 7s, 6 7s, minus 6 7s. It's ugly, right, with the 7s, but you'll see that actually they make it actually nice. So now I have to multiply with the transpose. So rows become columns. So the first row is now this column. The second row is now a column. And then the third row becomes the third column. Okay. Okay, let's work out this product. What's the top element here? So we have to do this guy times this guy, which is 9 7s plus. Then we do the next element with the next element, so this with this, that's 4 7s. And then we do 6 7s times 6 7s, plus 6 7s times 6 7s, 36. Hey. 3 7s and 3 7s is 9 7 squared, that's 49. Hey, what was I doing here? The denominator is 49, right? 3 7s and 3 7s is 49 over 49. 2 7s times 2 7s is 4 49s. 6 7 is 36 49s. Now, let's add this up. This is all common denominator, so 9 plus 4 plus 36. Oh, that's 94. This is 94 94ths. That's just 1. Great, right? So this is actually just 1. Good. Let's. I'm not going to work everything out and let you do this, but I'm going to work out this element. Okay. So now I have to take this row and multiply it with this column, right? Okay. So we get minus 18 over 49 plus 6 over 49 plus 12 over 49. Well, can you believe it? Minus 18 plus 6 plus 12 is actually 0. So that is actually 0. Now, please work it out for the rest. So I'm going to write here dot, right? So fast forward, I get that this actually is the identity matrix. So on the diagonal, if you would calculate these numbers, you get 1 and everything else is 0. That's cool, right? What does it mean? For one thing, it means that the matrix A is invertible and it means even that the transpose of A is the same as the inverse of A. Now the inverse, remember, of a matrix in general it's a bit difficult to find. I mean, you have to do calculation, you do this row reduction thing, or you can use a formula by the adjoint. It is not an easy thing to find. Transpose, that's nothing, right? That is just flipping things over. You have to just be careful that you don't get confused. So in other words, if you have a matrix whose inverse is the same as its transpose, that's actually a matrix that is very easy to work with. And things that are easy to work with, they often get names. So we get this is what we call an orthogonal matrix. So it's simply an invertible square matrix whose inverse is the same as its transpose. Of course, you have to prove often that a matrix is orthogonal, but once you know it's orthogonal, it means very easy. You can very quickly work with these inverses. Now let's think a little bit, what is happening here? First of all, what on earth has this to do with orthogonality being perpendicular? What does that all mean, right? Why would you call this way? Okay, so now let's get back at the calculation of our first element here. So this one here, this element, what do we do? Well, we took this vector, well, this row, and we multiplied it with this guy. Now, first of all, they are the same numbers, right? Why is that? Well, that's because this guy is the transpose of this guy. So that means that this row had become the first row had become the first column. So on purpose they are the same. We made them the same. Okay. Now, so what let's call U this first column here, 3 7s, 2 7s, 6 7s. So what is this? What we just work out is basically U dot product U, right? That's what we just reviewed dot products. But we had given a name to this particular dot product. If you have so remember the norm of a vector squared was the dot product of the vector. And the norm was that you take the square root of this thing. Okay? So what is we shown now in this calculation shows that, so in other words, this number that we calculate here was just nothing else than the norm squared of U. And we see that is equal to 1. But what is then the norm? If the norm square is equal to 1, and you have to take the positive square root, that means the norm was 1. So we actually, this U here is actually the property that its norm is 1. We call this a unit vector. That's the terminology from before. Okay. So what we have shown is, because this matrix is orthogonal, its first row or column, whatever you want to think about it, was a unit vector. Now the same is true for the second and the third column or row, right? I mean, it really doesn't matter whether I think of this as rows as column, because they are the well, yeah, I should have perhaps also said this, right? I calculated this product, but of course if I calculate this, I get the same thing, but just in opposite order, right? So this would be that perhaps it would be better if I work at this, let's write down this, what this would be. So now everything would be, sorry, I need a little bit, I'm going to erase a little bit here because otherwise I have not space. I'm going to copy things around. So let's write down what this guy is. This is, now we first write the transpose. This is the transpose, right? Two sevens, 6 sevens minus 3 sevens. And then we write the actual the original matrix. That was 3 sevens minus 6 sevens, 2 sevens, 2 sevens, 3 sevens, 6 sevens, 6 sevens, 2 sevens minus 3 sevens. I hope I didn't make a mistake. Okay. And this is again, let's now verify it one more time that everything, I'm claiming that this is again the identity matrix. So this is 0, 0, 0, 0, 0. So let's figure this out for this element. So what is this? This would be this row times this column. Okay, so let's call this the vector. Let's call the vector W is this column here. This is A, right? So we have now A at this side. Perhaps I should have done it from the start, but so let me now look at this same relation but from this side. So W is the vector 6 sevens, 2 sevens, minus 37 is the last column of my matrix A. And remember, very often we have situations where we have a vector that becomes a column in a matrix, right? This is, okay. So this W here. Now what is this term? Well, that is the same guy, just written in a row. So it's a transpose, okay? So, and I'm claiming this is 1. Let's double check. 6, 7 plus 6 sevens, 36 49s, plus 4 49s, that's 40 49s, minus minus, plus 9 49s, 40 49 49s, 1. Okay? So, again, I have that W, the transpose of W times W is 1, but we have now, by this formula here, that we can write this actually as a dot product. We get that the dot product of W times W is 1. And this is nothing as the norm squared. But if the norm squared is 1, then the norm is 1. So what we have shown is that the norm of W is 1. And remember, we did this already for U. U was this guy. This was the first column, right? Oh no, that was a different guy. Sorry. Yeah. So I should have started from this. So let's call this U and let's call this V. So ignore the previous ones. Let's work in this way. What I said is the same, but it's more clear if I do it this way. So I show now that if I take one of these columns, and you can now verify with the other that we have this property. So the columns of an orthogonal matrix are unit vectors. So this means that these are unit vectors, right? So these guys are unit vectors. But there is more going on, because this explains the values here. But what explains the zeros? Well, let's figure out what that is. So let's figure out how we get to this zero, say this 0. How do we get that? Well, we have to take the first row and then multiply that with the third column. Now let's double check. I'm going to just look at the numerators. I know the denominator is 49, right? So the numerators is 3 times 6, 18, minus 12, 6, minus 6, 0. Great. Okay, so what is this? Well, this is, let's write this down in the vectors. What is the red one? Well, the red one, okay, they're both red. So I'll make this in a different color. Let me get this rid of, yeah. Okay, so this is the red row times the purple column. The purple column is W. That's clear. What is the red one? Well, it is the transpose of A, so it's the transpose of the first column. So it's U, right? You see it, it's just U. So what I've shown now is that if I take, or rather U, this is a transpose of U. This is U transpose. So I get U transpose times W is 0. That's expressing the 0 here. But again, this is a dot product. This is the same as U dot product W, right? So it's kind of, I mean, how do you remember this formula? The formula says it's the same. If you write a big dot, then you don't have to transpose, and if you don't want to write a big dot, you have to transpose. I don't know. That's what it means. It really says they are the same. But what does that mean? What does it mean if a dot product of two vectors is 0? You remember what that means? This means that the two vectors are orthogonal. Okay? So, I showed you all this on an example. So let me now state the conclusions in general. So let A be an n by n matrix. And suppose it's an orthogonal matrix. Then the columns, the first thing that we notice is the columns are unit vectors. If you think of them as vectors, they're unit vectors, right? That was this calculation here that we did here. That was explained that we get ones on the diagonal. Now, what does the zeros tell me? And it says that different columns are orthogonal. That's the second property. That is this that we verified here, but I hope you can convince yourself this is now true. If you take any of the columns of A and you multiply them If they are not the same columns, then you get 0. And if they are the same columns, then then it's 1, right? That's what we just said, right? Remember, this is, so it basically says this: if you take an orthogonal matrix and you take columns, 2 columns, if they are the same columns, if you multiply, you get 1. If they're different columns, you multiply, you get 0. That's why we call this an orthogonal matrix. And this is a property of orthogonal matrices, but it's actually the other way around too. If you have a matrix that whose columns are unit vectors and whose different columns are orthogonal, then that actually is an orthogonal matrix. Because if you just think about it, what would happen if you multiply such a matrix with its transpose? And you'll see you get actually the identity matrix. Okay? Now you might say, okay, how easy is it to actually get orthogonal matrices? Okay, so that's one last thing I want to say. Well, 2 things. First of all, here's an example of an orthogonal 2x2 matrix. So, orthogonal 2x2 matrices. And you're going to be surprised what I'm going to do. Cosine theta minus sine theta, sine theta, cosine theta. So where theta is any real number, it doesn't matter which number it is. And so if you look at this matrix, I'm claiming it is an orthogonal matrix. Let's verify the 2 conditions, right? 1 and 2. As I said, it's the same. To be an orthogonal matrix is the same as these 2 conditions. So let's look at one column, this column. What is the norm of this column? Okay. How do you find the norm of a matrix? You take the square root of the square of the first element plus the square of the second element. You see where we're going here? This is the trigonometric identity. That's just square root of 1. That is just 1. So yes, we verified. So condition 1 is verified. I did it for one column, but it's clear that it's also true for the second column. Now, what about the second condition? Well, there are only 2 columns, so I only have to multiply the first column with the second column. Well, let's do that. How do you do that? Remember, it's a dot product, right? So it is multiplying the first with the first. So that is cosine theta times minus sine theta. And to that we add sine theta times cosine theta. Now, it doesn't take much of a genius to see that this actually cancels each other and that you get 0, right? So, yes. Here we are. So this is an example of an orthogonal 2x2 matrix. And in fact, every orthogonal 2x2 matrix is of this form. That's another thing, but okay. So they correspond actually, if you, these matrices, we said these are transformations, right? A matrix can be thought of a linear transformation. I said this way back here, right here. So you could try to visualize this particular transformation. How does it act on R square? Well, it's not surprising. Say that we are dealing with angles here. So the transformation that corresponded, I'm just going to give that for, we're not going to work with that. Just give some extra information. This is just rotation with angle theta. And rotation, we remember we do always rotate counterclockwise. So counterclockwise. Now this is not a course on geometry, so I don't want to explain this, but this is what it means. So it's not a weird thing. It's very obvious thing. Rotations are very common things, right? And the matrices. So what it says is, if you take a rotation in R square and you look at this matrix, you get actually an orthogonal matrix. Okay, and so what about making orthogonal matrices? And I'm gonna, let's see. Yeah, I'm gonna stop here. No, let me do it here. Perhaps it's better to say it here. Okay. Yeah. So what I want to do is now the following result. We eventually we're going to remember the title of this whole topic is diagonalization still, orthogonal diagonalization. Now the orthogonal is discussed a little bit. It has to do with orthogonal matrices, and diagonalization we know from before. and it had to do with eigenvectors. So I want to do the following thing. So suppose that A is a symmetric matrix, and right, symmetric matrix. And let's go now about eigenvalues. So let U be an eigenvector with eigenvalue. I'm going to give it I'm going to take two different ones, so I'm going to find, I wanted two different names, lambda 1, lambda 2 perhaps, but let me call it eigenvalue R, and V is an eigenvector with eigenvalue S. And the point is that the R and S are different, okay? So they are different. Okay, we know that this might happen, not always, but most likely we're gonna in a situation that we have two different eigenvalues, and so they have two different eigenvectors. Okay, I want to calculate the following thing: A U dot product V. Okay, now our first formula, all the way back up. No, not the first, the second formula, this one here, says that we move, because the matrix is symmetric, that's why I had this, I can move this to the other side, the A. So this is the same as U A V. Okay, so what I've used here, this is because A is symmetric. Remember, in general you would have to take the transpose, but we are symmetric matrix, so we don't do. That's the first thing. Now I haven't used that these U and V are eigenvectors, so let's use that. So what does this mean? So we know that AU is, what does it mean to be an eigenvector? It's just R times U with eigenvalue U, right? And this means that AV is, well, the eigenvalue is now S, so S times V. Okay, so let's plug that in. So we have RU dot product V is U dot product SV. Okay, just replace these things by that. All right. Now, R and S are scalars, or just numbers. And we know that those move around freely. We don't have to worry about them at all. Well, if you want, you can switch the S to the other side and you have to take the transpose of the S, but it's a 1-by-1 matrix, so it's symmetric, right? So in other words, this is just S times U V, and this is just R times U V. These are properties that we discussed about dot products. But this is a bit weird, right? So if I cancel, so sorry, these are vectors, right? So now U times V is a number. If I cancel that number in this equation, then I get that R is equal to S. But I just said that they're different. How can this be? They look the same now, because look, they give the same result. Unless, and this is something you have to get used to, is that such a thing is true, as I said, if I cancel out U times V. But I cannot cancel out U times V if that is actually 0 already. So from this, it follows that U times V must be actually 0. Because if it's a not 0 element, it's a number. If it's a not 0 number, I can cancel. So if it's not 0, I can cancel like this, and I see that R is equal to S, but that's not the case. So, in other words, I cannot cancel, and therefore this must be 0. Okay? That's quite something, right? It says that if you take two eigenvectors with different eigenvalues, then they are orthogonal. U is orthogonal to V. This sounds already very much like this, right? So if I put them in there, in a matrix, these two eigenvectors, and that's what we do when we do this P in diagonalization, then I get something that is orthogonal. Okay? So I'm going to stop here. I'm going to repeat it a little bit in part 2 when we're going to talk about orthogonal diagonalization.